um, could we live in a different universe? And the answer is, if we change the constants just the least bit, we don't exist. So there's two different approaches to the problem. First approach is a religious approach, saying God made the universe the way it is for us. The other approach is to say that we're one of an infinite number of possible universes, and therefore we happen to live in one that has all constants exactly right. And the problem with that, as far as I'm concerned, physics is obligated to come up with testable hypotheses. If you can't come up with some way of proving that, you're simply replacing one belief system with another. So this is one of the things I don't like about the multiverse idea. The basis of physics, as opposed to faith, is that faith, you can take it on faith, but physics is supposed to be testable and provable. So the idea that the multiverse might exist and that's why we exist, while it might be logical, I can think of no way that we could possibly test that. So that's my problem with the multiverse. Lyle, want to say something in there? Okay. A number of questions were presented to me concerning dark matter, dark energy. And one question was, what about the distant early blue galaxies at the beginning of the first thing that happened after the Big Bang in terms of large structure? Because of the higher density in the early universe, it's easier for massive stars to form. So the first generation of stars that formed, burning hydrogen to helium, were very massive stars, and massive stars burn out very quickly. So one of the things that happens with massive stars is they burn very bright, but they burn out very early. And they were the first ones to spew their material back into the interstellar medium when they went off as supernova, but they are no longer around. They basically either blew up as supernova or turned into neutron stars or dwarf stars. So that's what happened to those early blue stars. The mass is still there, but we can't see them anymore. Another question was, is there any new research on the origin of cosmic rays? Well, cosmic rays have long been known to be possible in the shock waves that occur in supernova. But the ultra high energy cosmic rays that we see have been traced to giant star clusters like the Coma cluster, where probably there are a lot of supernova going off in a short period of time. So basically the idea is that the super energetic cosmic rays sort of bounce from one shock wave to another, and in the process pick up energy. So they're surfing on these shock waves from numerous supernova going off in a brief period of time. Other questions, do we know the sum of all the regular matter in the universe? I would say the answer to that is no. Because what we see in luminous matter in spiral galaxies, for example, is not that the stars are actually making the structure of the spiral arm. The spiral arm is a density wave that's propagating out through the galaxy, and when it increases the density, that's where stars form. So we're not seeing all the matter in the spiral arms, and we really don't know exactly what the sum of that regular matter is. Another point concerning dark matter, we make an assumption when we look at rotation curves for galaxies that the galaxies are in gravitational equilibrium. That is, the stars at the outer edge of the galaxy that are rotating too fast are gravitationally bound. We do know, however, that all big spiral galaxies have somewhere near their centers black holes. And the stars in the vicinity of a black hole get accelerated at very, very high velocities. So some of those stars, or some perhaps fair number of stars, achieve escape velocity. So it may be that the catch is we're assuming the stars that are gravitationally bound at the outer edges of the galaxy are actually escaping. And it's very difficult to tell that with the measurements that we make. So it's possible that the problem is in the assumption that the reason the stars are rotating so fast at the outer edge is because they're gravitationally bound to dark matter. if we assume they might be escaping, then their velocities can be much higher. Problem with dark energy. We believe, based on measurements of the most distant quasars, that they're dimmer and their redshift is larger, which signifies they're going faster at large distances than the Hubble constant indicates. There could be other answers for why that is observed. For example, in the book, Tyson talks about cyanogen being excited due to higher temperatures in the past. As far as I know, no one takes into account the fact that the light coming from the most distant quasars is coming from a region where the density was higher. Therefore, there should be a gravitational redshift on top of the Doppler shift due to expansion. And I don't believe that's included in the calculations. So the bottom line is, I don't think we know the distribution of ordinary matter. I don't think we know the distribution of dark matter. I'm not even sure that dark energy is something that exists. Again, the tenet of science is that it all be provable. We've been looking for dark matter for a number of decades, and so far no likely candidates have shown up. Okay.
Okay, so I put a gentle reminder in the chat that any questions or concerns or dialogue can show up in the chat, or at a point like this one, if you're ready, just hop right on.
Okay, I'll wait for questions. A couple of other comments. Tyson makes an interesting statement concerning what part of the universe we can see now and what part of the universe we will not be able to see in the future. But one of the things that he apparently overlooks, and it's in the scale, universal distances scale to 1 AU, the present size of the universe is about 93 billion light years across. That's because we take into account the rapid expansion during the inflationary period, and also it takes into account that the most distant things we can see are the first galaxies that formed at about 13.3 billion years ago. If we take the most distant galaxy we can see now, which is a galaxy called EGS ZS8-1 at 13.1 billion light years away, and we figure out the fraction that corresponds to in terms of the 93 billion light year diameter universe, we're only seeing about 2% of the universe now. So our view of 98% of the universe is restricted forever because there's nothing to see, or it's outside our light cone. So the idea that somehow the universe is going to get a whole lot darker in a hurry is erroneous. It will get darker slower. Okay, any other questions?
Yeah, we've got a question from Kevin. Does the idea of outer stars reaching escape velocity imply an enormous number of stars departing all galaxies?
Well, we actually have identified stars between galaxies that are moving at very high speed. We believe that galaxies evolve the same way planetary systems do.
It looks like it got logged in at Sean.
I didn't get that. What was the question?
No, there wasn't a question. It was just an oops. Well, Paul, last year we talked about that there's some people who hypothesize the universe is going to continue to expand infinitely, but there were some views, and Stephen Hawking referred to some ideas that maybe it'll stop and contract. And I just wanted to sort of check that idea with you again.
Well, the problem is that we try to solve the simple problems, or we simplify complicated problems to the point where we think we can solve them. In the case of the universe, recently they discovered an arc of supernova, an arc of black holes that's 3 billion light years long. Now, that says the universe on large scales is not uniform. When we can see structure like that over that length of distance in the universe, it says our assumption that it's homogeneous and uniform is maybe not correct. So saying what the universe is going to do depends on our assumptions about the distribution of matter.
Okay, let me ask another question from Lewis. Is the only evidence for dark matter the otherwise unexplained gravitational effects at large scales? Or are there alternate explanations?
Yeah, there's some modified theories of gravity that introduce other terms that show up on large and small scales that the parameters can be adjusted to fit the observations. Again, the whole idea of science is it has to be something testable and provable. A conjecture does not make it science. The thing that makes it science is the repeatability and provability of the assumptions. One of the other things that Tyson talks about is the cosmological constant, the idea that dark energy is simply a reflection of the vacuum energy that exerts a pressure opposing gravity. But Tyson points out that the calculations from the best minds on the subject come up with an error of a factor of 10 to the 120 power in the value of the cosmological constant. The cosmological constant that they calculate should result in everything flying apart so fast that nothing forms. No atoms, no people, or anything. Now, an error of 10 to the 120 power could be swept aside by political career politicians as a minor miscalculation. But to physicists that work on the 8th decimal place of some calculation, that would be called a colossal blunder. So clearly we don't understand something. And we don't understand it big time.
So I had a question about dark matter. In my reading, it sounds like the theory was it had to be a halo of dark matter around a galaxy. So how does modern physics think it's distributed? Is it outside the galaxy, separate?
Okay, well, let me go back to what I said earlier about the assumption that the galaxies are in gravitational equilibrium. If a black hole at the center of galaxies is flinging stars out, then those stars at large distances will have a much larger velocity than what their orbital velocity would be based on the amount of matter that you see in the galaxy. So therefore, the only way to reconcile that with an equilibrium situation is to say that there must be dark matter outside the normal matter of the galaxy that's causing them to be gravitationally bound. If they're escaping, then all bets are off. As I said, we do see stars that have been thrown out of galaxies that are still burning in intergalactic space.
So is our own star gravitationally bound? Because we're kind of on an edge, right?
Well, we're actually not that far away from the center. We're sort of in the suburbs. This also has to do with how you define the extent of a galaxy. If you define the edge of the galaxy in terms of drop-off density of stars, then you can, for our Milky Way galaxy, you can come up with numbers between 100,000 light years and 200,000 light years. So where's the drop off? Where's the cutoff? If you define it in terms of the halo of dark matter, the galaxy is a lot larger than if you simply go by the luminous material.
Paul, so the universe is so incredibly old. How could anything not be in gravitational equilibrium?
Well, our solar system started off by having roughly 10 times as much material orbiting the sun in the protoplanetary disk than we have now in all the planets. So our solar system has been flinging out material or moving material into the sun since its inception. We've recently had 2 interstellar visitors that came into our solar system from outside. We can tell by their velocity. So they were flung out of the solar system somewhere. We now have 5 objects leaving our solar system that we contrived to leave our solar system by playing gravitational billiards. Pioneer 1, Pioneer 2, Voyager 1, Voyager 2, Pioneer 11, Pioneer 12, and the spacecraft that flew by Pluto, New Horizons. So we did that not by rocket power alone, we did that by gravitational billiards. Drop them behind a big planet that's moving fast and out it goes. And presumably there are a lot of objects whizzing around between the stars that got expelled from planetary systems in other solar systems. So it's a gravitational equilibrium in a sense, but it's a dynamic equilibrium where some objects are attaining escape velocity. We like nice, neat answers that say everything is tidy.
And Paul, just to be clear, when stars escape a galaxy, like where do they go? Do they just sort of hang out without gravitational currents pulling them in?
Well, we know, for example, in our own galaxy and from nearby galaxies like Andromeda, we can identify, now that we have really precise measurements of stars' positions and their velocities, we see some swarms of stars pretty much moving the same direction that came from a dwarf galaxy that the Milky Way gobbled up. We have numerous dwarf satellite galaxies right now, and some of those will get gobbled up by the Milky Way over the course of billions of years. In fact, we're scheduled to collide with Andromeda at some point in a couple of billion years. And when these small galaxies, dwarf galaxies, collide with the Milky Way, it's not like there's a big smash up of star on star. The distance between stars is so great that they simply gravitationally merge.
Would you talk a little bit more about what happens in a gravitational merger like that?
Well, for a while, we see the dwarf galaxy as a coherent entity until mutual gravitational interactions among their stars and the stars of the Milky Way start to randomize that. So it's not like it goes flat. It's more like a long-term interaction over many millions of years or even billions of years as these stars get assimilated. We believe that most large spiral galaxies like the Milky Way and Andromeda actually built by gobbling up their neighbors. And we also see out in the cosmos really strange looking distributions of stars with things that look like streamers and tails and so on. And these can be reproduced by simulation of gravitational interaction among neighboring galaxies. There are bridges of stars streaming between 2 galaxies in some cases. So this is something that has been going on, especially when the first galaxies were being formed and the universe was denser than it is now. The chance of interaction was much greater back then. Like I said, it's not a splat. It's more like a very gentle merger.
Thank you. I've got a question, another question from Kevin. If we're looking at only 2% of the universe, could we not be making the assumption that the universe is either flat or open or closed? In a similar way, we might assume the Earth is flat because of how much of it we can see.
Well, the problem really is we have no way of knowing what's beyond 13.3 billion light years. So it could be doing all sorts of strange things outside of that affect the stars, the galaxies we're looking at, or the quasars. We have no way of telling that.
Another question in the chat. By gravitational equilibrium, do you mean that the objects are in closed orbits? Then any object traveling at a sufficient speed is not in equilibrium?
Well, there's a fairly convenient way to define what a closed system is. It's a system in which even the most distant objects are gravitationally bound to some central object. So for example, we have an arc cloud that we've got a comet coming in now from one light year. Between stars, like the distance to our nearest neighbor is about 4 light years. Presumably there's an arc cloud stretching out from our sun halfway there, and there's an arc cloud around that star that stretches to the junction. Objects, since our star and the nearby stars are moving relative to each other, then it's a mixed master on a very large scale. We attract part of the arc cloud from other stars as we pass by. Very, very gentle nudge, but it happens. So interstellar material gets interchanged between stars, as witness the 2 objects that we've recently identified. In fact, in the course I taught on solar system physics at Rice for nearly 40 years, I predicted eventually when we look close enough, we would see objects coming in from another planetary system. It's just we didn't look carefully enough and didn't have the capability of looking with high precision for those objects. Now we can see them.
Paul, I've got another question I'm going to put in the chat. And this came from last week when we were talking about sort of choices between like atheism and some creative force in the universe. And the question says that the asker has heard that atheism is the more probable choice, but why should either choice be more probable than the other? In fact, it seems that the invocation of the multiverse requires a multiplication of entities, making it a violation of Occam's razor.
Well, Occam's razor is not a law. It's a sort of a generality. So as I started in this discussion, proposing an alternative that replaces one belief system with another is not what physics should be doing. I mean, there may be scientists that don't like the idea of religion, but replacing it with something that's no more provable than religion from a physical standpoint, as far as I'm concerned, is not a step in the right direction. A good example is this problem of a factor of 10 to the 120. If we add up the total number of seconds since the Big Bang, that's a number about 5 times 10 to the 17 seconds. Think about how much bigger 10 to the 120 power is compared to 10 to the 17.
I know it's a little bit of a stab, but Neil does say in his book that there's this interesting way to view that people are made of stardust and essentially are like the entities in which the universe can explain itself. And I wondered what you thought of that sentiment.
Well, as I said when we started this course, the most profound thing that Neil says is the universe is not obligated to make sense to us. Or another way of saying it, from a religious standpoint, God doesn't owe us an explanation. So one interesting question is, when we start running into real barriers like factors of 10 to the 120, our search for dark matter, dark energy, trying to make sense of spooky action at distance entanglement, we're starting off with a basic philosophy that somehow we should be able to understand all these things. But again, there's no guarantee. It may be that there are things that we will never be able to understand, just like there are things we will never be able to see in terms of our own universe. So we're kind of vain. We're made of stardust, created on planets that somehow we have arrived at the conceded conclusion that we're supposed to be able to understand everything.
Question from Lewis Paul. How do we know that extrasolar objects are in fact extrasolar? Is that by their velocity or by their light shift?
By their velocity. We know what escape velocity from the Earth's orbit is. So when you see an object coming in moving much faster than that, it came from somewhere else. It's not gravitationally bound to the sun.
Paul, can you explain a little bit about the 10 to the factor of 120 difference and what the difference is between?
Well, there's an effect called the Casimir effect. If you separate two metal plates by a very small distance, there's a force that pushes them together. The idea is that putting them at close proximity tunes it like a tuned cavity in electronics to only allow certain wavelengths for the vacuum fluctuations to occur. Therefore, there are fewer between than there are from the outside. Therefore, the two plates should be pushed together. That effect is actually observed. The problem is it's a very, very weak effect. If you calculate from quantum physics the number of different wave modes that are possible in a vacuum, you get a number that Tyson says is a factor of 10 to the 120 power different. So as I said, that would be considered in physics a colossal blunder. So clearly we don't understand something. In fact, it's becoming more clear there are more and more things we don't understand.
So on a different subject, I was reading about a galaxy that doesn't appear to have dark matter, and it looks like this giant fuzzball that you can see through. Do you know anything about that and what the theories are on that?
Yeah, there are attempts to categorize galaxies, especially spherical and small galaxies, in terms of the ratio of normal matter to dark matter. To understand it, best thing to do is study it in as many different varieties as you can. Now, one big difference is that a lot of these small spherical galaxies do not have black holes. So they could well be in gravitational equilibrium. Therefore, we conclude there's no dark matter. I mean, dark matter is not something you observe. You observe stars doing things that your assumptions lead you to believe there's something else there exerting gravity.
That's really cool. I had not thought of it that way.
Well, whenever you get such huge discrepancies, that's a clue that you may be clueless. There's some issues that have to be addressed.
So can you talk a little bit about why the dark matter? I can kind of wrap my head around the different observations that they've used dark matter to explain. How about dark energy? What observations are there that's explaining?
Well, let's go back to Einstein's general theory of relativity. Einstein introduced a cosmological constant. The idea was that the universe was static. It wasn't until sometime later, a couple of decades later, that Hubble showed the galaxies were all receding from each other. So Einstein said, well, I don't need the cosmological constant anymore. So he tossed it out and said it was his biggest blunder. Well, now they see at great distances what appear to be quasars that are moving away faster at larger distances than they thought fit the Hubble idea. So therefore, something was accelerating these distant objects. And conveniently, Einstein had already come up with a cosmological constant. So we plug in cosmological constant given non-zero value, it at large distances acts as a pressure that pushes out against gravity and accelerates objects at large distances. Now remember, there is no way of saying that something outside our region of observation might be pulling them rather than something inside pushing. We can't see what's out there, so we have no idea what is going on.
So Paul, the expansion that we observe at large distances, that is how is that interpreted? Is that as an expansion of space-time itself, or is that the movement of objects through space-time?
Well, we observe peculiar velocities among most objects in the visible universe. That is, objects are moving relative to each other with an additional velocity above and beyond the Hubble expansion. One of the problems, for example, is we know that there's something on the other side of the Milky Way from us. It's called a great attractor, and it's pulling us and a number of other nearby galaxy systems toward it. We have no idea what it is. We can't see it because it's obscured by the Milky Way disk itself. We also know that clusters of galaxies orbit each other and are gravitationally linked over very large distances. We don't know what this 3 billion light year arc of black holes is, but presumably the black holes are at centers of galaxies. So there's structure on a scale that's comparable to the distance we can see. Okay, that's the question. You can't see the galaxies. It's because the galaxy's stars are not bright enough for us to see at those distances, but the quasars are bright enough for us to see at those distances. So presumably every one of the quasars has a galaxy around it. I'm looking at my list of questions. I think we've covered most of them.
Are there quasars that are closer to us than the ones that are so far away that are perplexing us?
Yeah. We believe from observations that almost all large spiral galaxies have black holes. And a black hole is basically an active, or the quasar is an active black hole that's gobbling up material and heating it to very, very high temperatures and producing jets that go out into intergalactic space. So there's within several 100,000 light years of our galaxy, we see a few other quasars.
Can a black hole eat or take over another black hole?
Yeah, in fact, LIGO, the gravitational wave detector, has detected exactly that happening. Seen a merge of two black holes. Okay, so that's what happens. Two black holes merge to become one. And according to recent measurements, they obey the rules that Hawking's laid down about the size of the event horizon after the merger.
Antha, I know you've prepared some of the intersections between what we're reading and some sort of thoughts about faith and faithful living. So I wanted to go ahead and see if you're ready to make that transition with us.
Sure. So one of them, Paul actually already started to address from the science end, which is that thinking about the future civilizations that can't see as far as we can see now, Tyson says, "Behold my recurring nightmare. Are we too missing some basic pieces of the universe that once were? What part of the cosmic history book has been marked access denied? What remains absent from our theories and equations that ought to be there, leaving us groping for answers we may never find?" And so that made me think about what if some of the earliest creation is and always will be hidden from us? And what does that say about our universe and about our God?
I think that's one of the things. It's a good question, and my feeling is kind of comes back to a point that Paul made earlier, that we have this belief that things are explainable, and I think it's a faith, and it's a faith that I have, that our knowledge will continue to expand and our explanations will get better as time goes on. But that's only a faith, and I think it's a faith in what I would call a good God, that God wouldn't have created us to make this journey that we've been on for so long, if we weren't going to continue to progress that way. If we're to eventually come to some spot where we just can't make any more sense of it. And so I think there's a line in Tyson's book where he say we're waiting for the next Einstein, for the next great mind to come along that pulls up the next curtain. And I have a faith that will happen, but it's only a faith, and it's a faith in a good God that will allow us to do that.
Paul, you had mentioned, an observational limit at the extreme macro end, that we have essentially a light bubble around us that we can't see through, but there is universe beyond that light bubble. I also have a memory that there is basically an observational limit at the extreme lower end. Is that a true statement? I mean, the Heisenberg uncertainty principle, you get to a certain level and you simply can't make predictions about individual pieces of the universe anymore?
Well, we're limited by several different factors in probing the smallest scale. One of them is that when we talk about what happened in the early universe, we believe that there was a direct transition from the radiation stage, the light era, to quarks and gluons. Now, we believe that for no other reason except we have no accelerators to get us to higher energies than where we see quark-gluon soup. I'm reminded about early map makers when they were first trying to draw maps of the world. If they got to something that they did not know about, they'd call it terra incognito, unknown land, and then here be dragons. So we're at the point of here be dark matter, and here be dark energy, and here be spooky action at a distance. It's terra incognito to physics. And whether we can get beyond that depends in large part on the experiments that we can do and the experiments that we can predict might be done. For example, they're talking about putting an accelerator on the moon that goes clear around the moon. Now, I don't know how that fits into our multi-trillion-dollar budgetary constraints, but I suspect we can't afford it. So here be dragons.
All right, so I've got another question. This is a quote from a book called The 4% Universe. Astronomy is full of Homo sapiens humbling insights, but these lessons in insignificance have always been at least somewhat ameliorated by a deeper understanding of the universe. The more we could observe, the more we would know. But what about the less we could observe? What happens to our understanding of the universe then? What currently unimaginable repercussions would this limitation and our ability to overcome it or not have for our laws of physics and our philosophy, our twin frames of reference for our relationship to the universe? So I think that's more on the same theme, that if our universe really is only 4% the matter that is us, and we can't know the rest, what does that say about us and our universe and our God?
Well, again, I go back to the statement that Tyson makes. The universe has no obligation to make sense to us. Our God does not owe us an explanation. And if you believe that, then maybe we run into a brick wall. Maybe that's why we don't hear extraterrestrials talking to us. I'll talk about that next time.
Paul, can I ask you a weird question about quantum entanglement and like the spooky effect?
Yeah.
Right. If it's happening with quarks, is there any kind of bridge that makes between human beings who, often like to act tribally and separate? I mean, is the universe kind of begging us to course correct that mentality of being able to cut ourselves off from one another?
I think that's a question you can answer better than I can, Mike.
I think you're giving me more credit than you should.
Well, I'll tell a quick joke that sort of reveals why we have the problem we have. This is a story that a lot have probably heard because it goes back many years, but it seems like many years ago, the dairy industry in Holland was in trouble because the cows quit giving milk. So the head of the dairy industry went to the head of the government and said, we got to do something about it. So the guy says, well, I know a guy at Delft University that has in the physics department. So they can solve the problem. So they go to the head of the physics department at Delft University and said, here's $1 million guilders. Tell us why the cows aren't giving milk. He said, we'll work on it. So he spends a year working on it, finally calls the head of the dairy industry and says, I have a study for your attention. So delighted, the head of the dairy industry goes and gets the book and opens the page and starts reading. It says, assume cows are spherically symmetric, emitting milk equally in all directions. So assume galaxies are in gravitational equilibrium and make whatever other assumptions you want to make. As I said at the start of this, we don't solve real problems. What we do is we simplify problems that are real problems to the point we know how to solve them, and then say by inference, it must be the right answer for the real problem.
I guess perhaps another way of stating that is we build models that are trying to extract certain properties of the real world, and we draw conclusions from the model. However, it doesn't mean that the model is perfect with respect to the real world that we're trying to do that.
Well, there's a basic principle of exploration that's called perturbation theory. The idea in perturbation theory is you solve the simple problem and then you slightly perturb it with the understanding that nature doesn't make huge jumps in solutions. So if you know what the solution is for the simple problem, by making small perturbations, you can therefore address the more complicated problem. And this works up to a point, but after fourth or fifth iteration of perturbation theory, it's anybody's guess whether you got the right answer or not.
Oh, that's true, and there's hopefully it works in a lot of cases, but then there's chaos theory. There's
yeah, but the butterfly effect
on initial conditions.
Yeah.
I'll interject as an engineer. We like to say all models are wrong, some models are useful. So.
Hey, so the way we say that in theological speech, and this is from Gregory of Nazianzus, concepts create idols, only wonder really knows.
Is that mysticism, Mike?
Yeah, which is way over my head.
So I had two things. I wanted to go back to Anthony's question about if the universe is truly only 4% ordinary matter and the rest is unknowable. What does that say about us? I just find that mildly terrifying. And I'm just kind of hoping, Paul, that it's because we don't understand gravity. And you had mentioned this earlier. Any ideas on that? Gravity business and gravity waves moving at the speed of light business?
Well, one of the great things was that Einstein's predictions about gravity waves have been verified by LIGO. So the laser interferometer, that it actually measures changes in dimensions of space, a fraction of the width of an atom.
Tiny. So where does it leave us with this 4% problem?
Well, first of all, I'm not sure about the 4%.
So, Paul, if I understand what you said earlier, I mean, the denominator in that 4%, that in and of itself came from an assumption about inflation, didn't it?
I'm sorry, say again?
That the denominator in that 4% that you talked about earlier, based that the universe is, I believe, 90 plus billion light years in diameter or in radius.
Yeah, okay.
That comes from an assumption about what happened during inflation. Is that correct?
Yes, she's ready for it.
Yeah, the point is there are models that incorporate every phase from the Big Bang through the present, including the inflationary phase. So the 93 billion light years is the result of the integration of all those different expansions. And as far as how accurate it is, well, you have to compare the background measurements. For example, the irregularities in the black body radiation to tell what the scale size of things were and what they are now. So it fits. That doesn't mean it's necessarily correct. It just means we have some confirmation that the ideas have merit. One interesting thing would be if we finally do communicate with another intelligence, what do they think? Would they have religion? Would they have believe in particle wave duality? Would their theory of gravity be the same as ours, and so on?
I think they would be just as confused as we are.
Well, it's good for physicists to be confused. Back in the 1930s, some physicists declared that we already know all the physics there is to know. And then along came fundamental particle physics that came up. I think there was one physicist that said, who ordered that when they discovered the muon? We didn't need it. The difference between theory and experiment is that theory is conjecture, experiment ruins a lot of conjectures. Confirms some, but ruins more.
If I could just move back quickly to the faith questions. One thing that's helpful for me is to think about when any one of us look up at the stars at night, do you feel a sense of belonging, of spiritual belonging, or do you feel like a tiny ant lost in infinity? Antha stated this in her question as enjoining a story already in progress.
Was that a question for me or for Mike?
For everybody.
I think that when you look outwardly into the infinite cosmos, it's easy to get lost. But to find yourself, I think that once you look inwardly and discover the things about yourself and discover the relationships that you have and the value of those relationships, I think that's when you start finding value in yourself. You don't feel so lost.
I think it's a little bit of both.
It was an interesting statement somebody made earlier. I think it was referencing back to the star stuff statement that life is the universe expressing itself. You know, if you allow that somehow these combinations of carbon and hydrogen and oxygen and sulfur and phosphorus and calcium and iron, et cetera, and so forth, somehow became arguably self-aware and able to contemplate and extrapolate from observation interesting theories going out beyond the observable universe and below the observable universe, that is an interesting place to be. It kind of puts your life and your experience as a sentient being in an interesting perspective within the cosmos.
Well, I guess from my point of view, that, you know, astrophotography is a hobby of mine, and I really love going outside and looking at the sky and the stars and going and watching for meteors for a couple hours, and it is a feeling of for me, like, deep connection with this enormous, you know, amazing, you know, it's like beyond human comprehension, I think, how big our universe is and all the different parts, and yet I'm part of it, and I'm there, and I'm in it, I'm embedded in it, and it's just for me personally, it's a very powerful feeling of connection to go out and look at the stars.
Can you all hear me? Two things. I look at quantum physics and I feel really big And I also feel that God is everywhere. And, you know, God, for me, seems to permeate the universe too. And the scale, it seems to me like we're in the middle of the scale, or it just doesn't matter.
Rhonda, I have a quote from one of my favorite Richard Rohr books about God being everywhere, assessing the divine force field. As we tune our hearts to greater perception, we'll begin to experience God almost like a force field, to borrow a metaphor from physics. Gravitational, electromagnetic, like light itself, they all work. And we're all already inside this force field, whether we know it or not, alongside Hindus and Buddhists and every race and nationality. These man-made force fields pale in energetic strength to the divine force field, which is all-encompassing. It's a nice metaphor. I'm not sure how far we could push that, but I think that's one thing that science does give us, is some ways to express ourselves about the ineffable sometimes.
Well, I want to thank you again, Paul, for guiding us. Thank you for your patience with questions, especially that I asked that I probably shouldn't. And thanks all for joining the call. And I look forward to seeing you next week. Really, really grateful for Antha and for Lyle adding in. And remember that you'll see documents in the e-news that Paul created last year that go along with what we're doing, like a time scale, and Antha's created a time scale for dark energy and dark matter that'll be in the e-news as well. You'll find that on Wednesday, and they're PDFs that you can just pull right up. Thank you, everybody, and really looking forward to seeing you again soon.
Thank you, Paul. Thanks.